Thanks for being here today. I hope that if you had to follow the second session in remote, everything went smoothly, otherwise please tell me. And so today we're going to start, let's say, non-Euclidean things, so more geometric things, and talk about graphs. But as we are going to see, it's a bit of a slightly misleading term, because when you think graphs, probably you think discrete objects. And the whole spirit, of the next 5 sessions is going to be that discrete and continuous descriptions of geometric spaces are just two sides of the same coin. And so we're going to mix continuous intuitions into the discrete sessions, and discrete intuitions during the continuous sessions of manifolds, etc. So just as a recap of the first 2 lectures, if a few people still arrive, and just in case you didn't follow everything on YouTube, in the first session, in the introduction, when we were like 70 in the room, we saw 3 things. So first, that AI, machine learning, is just about designing model and fitting them on data. And so that we strive to develop good models that are going to be trainable on the data that we have. And most importantly, we've seen that there are good criterions to choose what is a good model. And firstly, I would tell you that a good model should be simple and accurate. So usually you have a trade-off. And how far you go towards accuracy to the detriment of simplicity usually depends on your application. But most importantly, you should always remember that you want your model to be as honest as possible about hidden biases, about just the prior that you are implicitly putting into your decision rule using your equations. And maybe that the most important thing to have in mind is that having a simple model allows you to understand it at a deeper level and thus to be creative. Okay, and we saw the thing about shape spaces with triangles, and then some texture synthesis, like ideas that come naturally if you understand convolutional neural networks as something more than just a black box. So then last week, we studied essentially baselines on flat vector spaces. Okay, so I insisted a lot on the fact that if you want to do good data science, if you want to do good machine learning research, you should talk to domain experts. So in my case, doctors, and that's why we're here. And ideally try to make it personal, make it a recurrent event, just have coffee breaks with doctors to understand the global context in which you do your research. And we've seen that the best case scenario, so the ideal scenario as a data scientist, if you want to actually solve a problem, is that maybe the doctors already have high quality features, very informative. And so in this case, if you can take your decision using only a few columns of your tables, then you have access to extremely well understood baselines. So we talked about trees, about k-nearest neighbors, about linear regression. We talked a little bit about vanilla neural networks. Okay, we saw that in practice, they are very unwieldy, so due to non-convex optimization issues. So maybe, at least for simple problems, it's not the ideal solution. And finally, we talked about kernel regression, okay, method that allow you to specify the smoothness or let's say a class of function for your decision model. And so in practice, those baseline, essentially the things that are implemented in scikit-learn allow you to work efficiently on easy problems. But now, what about the difficult things? Okay, because I started the lecture by telling you that geometry was about countering the curse of dimensionality. Okay, we saw this table, and we understood that machine learning, as opposed to standard statistics, is about doing regression or classification on tables, data sets that have more columns than rows. And this, we didn't really address that last week. So if you remember, I told you that the curse of dimensionality first has a statistical interpretation. I don't know if you remember very well these comics, but essentially it was a story about someone who wanted to find a correlation, or who wanted to know if there was a correlation between jelly beans, so think like Haribo gummy bears, and acne. Okay, and we saw that if you just have access to the daily consumption of jelly beans, so just one indicator, and try to correlate it with acne, then you're likely to find a non-significant correlation and think that, okay, it has no impact. But we saw that in today's context, where when we have access to so many information about people, maybe we have access to the color of their jelly beans, of the color of their Haribo gummy bears, then we are tempted to make many independent statistical tests. And when you do that too often, you overfit on spurious correlations. So, and this is a main danger that we have to fight, when we do machine learning. And so all the classes in the MVA, all those lectures, they are about trying to find and teach you models that shouldn't overfit this easily. Okay, so maybe a second example, you have a full website dedicated to spurious correlations. And if you go there, you will find, for instance, that across the last 20 years, the number of people who drown by falling into a pool is very highly correlated with the number of films that Nicolas Cage starred in. Okay, and so that's a typical example of I have one variable of interest. So like who on earth is drowning into a pool by falling into a pool. And then I have a massive data set with as many columns as there are random factoids on the internet. And then just by random chance, someone was able to find like these near perfect correlations. Okay, so we saw that when you are in this situation, you have at least two simple workarounds. The first one is to try to do sparse, to try to use a sparse regularization method, like decision trees, lasso regression, if you're taking classes on this, like signal processing and convex optimization. But this is usually not very suitable for the type of signal processing and image processing tasks that we're interested in, usually in the MVA. And the second alternative is to try to regularize the decision by demanding that your model should be smooth. Okay, and this is what polynomial regression or kernel regression is about. Okay, we saw that maybe you have your feature space, you can define a Gaussian function, x of minus Euclidean distance, the squared Euclidean distance, and essentially you fit your model by saying, okay, I want to find a linear combination of Gaussian functions that fits my data. Okay, and this seems like a good idea, at least when we study it on 1D and 2D data sets. Okay, and that's what we saw last week. But now I have a question for you. What does a normal distribution look like? Okay, what is the intuition that we should have about normal distributions? So it seems like a stupid idea because for the last 5 years of your curriculum, you've seen that every time we talk about a Gaussian distribution, we draw just a Bell distribution. Okay, so something like a curve, a flat curve in 1D. So here it's exponential of minus x squared divided by 2. You have a bump, like nothing special, at least in dimension 1. Now, what about dimension 2? Dimension 2, here, it's a density plot of normal distribution that is centered here at 0 and first direction 1, 2. Okay. And now, what about dimension 3? Like, what does a normal distribution in dimension 3 look like? Maybe the picture that you have in mind, is like a 3D plot with kind of a bit like a sun, and then projected in the 2D plane. But this, you can argue that this is not, the picture that you have in mind is not a 3D normal distribution. It's just a 2D normal distribution because you had a 3D object and you projected it in 2D. And actually the properties of normal distributions are that if you project, by integrating your normal distribution from an n-dimensional space to a 2D plane, you just recover a 2D normal distribution. So this picture is highly misleading, about the reality of normal distributions. And maybe another way of seeing that this is misleading is that what what is the main difference between a space of dimension 2 and a space of dimension 3? Like if you had to guess, like how do you see, it's going to be one of the main topics of the lecture today, like what is dimension? Okay, like maybe the most intuitive, not the most intuitive, but the most mathematical answer is to say that in dimension 2, the volume of a sphere grows in r squared. The sphere of radius r grows in r squared, and so the volume of a shell is proportional to r. Whereas in dimension 3, the volume of a ball grows like r at the power 3, and the volume of the outer shell grows like r to the power 2. Okay, and so what you see is that basically here we know that the Gaussian distribution has a high density at the core, when r is small, but also and a smaller density when r grows. But what happens in high dimensional spaces is that the volume of the set of points such that r is close to 1 is grows exponentially, is much larger than the volume of the points such that r is close to 1/2 or close to 0. Okay, like in dimension 1, if you take a length area, like you have as much area here than you have here. But in dimension 2, basically this circle is much smaller than this circle, and you can intuitively understand that this is going to be much worse, okay, in dimension 3. So what happens in dimension 3, 4, 5? Okay, so here I'm doing lots of hand waving, and so maybe we should try to do some quantitative plots to understand what is happening with Gaussian distributions in dimension 3, 4, 5, 10, 100. And so this is easy to do. Okay, what does a normal distribution look like in higher dimension? Maybe we can just write a simple Python script where we're going to draw at random a data set of 100,000 points, X, with D features. Okay, so this data set is just a big array with 100,000 rows and D columns. Okay, so D equal to 1, D equal to 2, that's what we saw earlier. And now we can do D equal to 4, D equal to 9, 16, 25. Okay, so I draw just this completely random Gaussian noise. And then I compute on every row of my data set, I just compute the Euclidean norm. So the norm of X is the square root of essentially x1 squared plus x2 squared plus xd squared. And now I plot a histogram of this quantity. And what do we see? Okay, we see that for d equal to 1, we just retrieve our usual Gaussian distribution. But for d equal to 2, already you see that actually you have very few points that have a low, that have a 0 norm. And that's because even though here it's in yellow, it's bright. It's just 1 pixel. Whereas when r is a bit larger, you have maybe 10, maybe 50 pixels. Okay, so this is where this curve comes from. And now, if you do the same thing with a table that has 4 columns, you find this purple curve, d equal 9, this curve, d equal 16, d equal 25. And so we see a shift towards high values. Okay, so a normal distribution in dimension d has seems to have here an average norm that is on the order of the square root of d. And this you can understand that if you write, if you look at this equation, because here, okay, just looking at the formula which is inside the square root, we recognize the sum of d random variables, so x1 squared, xd squared. All those random variables, they are independent. Okay, this is the way I generated my table. They are identically distributed, and they have a mean 1. Okay, and this is just a definition of a normal distribution, variance 1, and mean 0, it means that xi squared has mean 1. Okay, and so here, I'm just taking the square root of d independent variables of mean 1, so the sum has mean d, And so I take the square root, I get a random variable of mean square root of d. So maybe, you know, if I want to plot this for d equal 100, okay, maybe I should normalize things. Now that I've understood that the order of magnitude of my variable is d, is the square root of d, I can plot the same histogram, but not of the Euclidean norm, but of the scaled Euclidean norm, 1 divided by square root of d times the norm of my rows, x. Okay, so I still have 100,000 rows, x. Okay, sorry about this interruption. Okay, so just what we saw is that, okay, it made sense to consider the norm of the rows of our normal samples divided by the square root of d, okay, because it's something that should have a mean 1. And if you look at the histograms, okay, so for d equal 1, it doesn't change anything, but for d that becomes increasingly large, okay, we observe a kind of Bell distribution centered around 1, and with a standard deviation that grows smaller and smaller as we increase d. Okay, and this also makes sense because you can write 1 divided by the square root of d of the norm of x as a square root of the average value of xi squared. Okay, and so this is the average value of a sum of independent variables. And so according to the central limit theorem, you know that this converges towards a normal distribution centered around the mean, so 1, and with a standard deviation that grows smaller and smaller as d increases. Okay, so this is a 1D plot that already tells you that something strange is happening in high dimension, which is that a high dimensional normal distribution is kind of concentrated around a single value in terms of distance. Okay, but this is just for the norm of x. So what happened? Maybe a better way of explaining that to you is to try to draw the same plot but in dimension 2. Okay, so here what I'm trying to convey, so what I'm showing you is a 2D histogram of a normal distribution in dimension d. Okay, and once again I have rescaled the features to ensure planar projection. So here, okay, so what I'm displaying is that I have my big random array with 100,000 rows, d columns, and I pick the first 2 columns as my x and y coordinates. Okay, so if I was just displaying my x and y coordinates, you know, to do my histogram, I would just be displaying to you a 2D normal distribution. So to try to convey the intuition of what happens in the high dimensional space, I rescale the 2D vector x1, x2, so that it has a norm which is actually that of the high dimensional vector x. So the formula looks like norm of x divided by the norm of the projected 2D vector, and I still keep the square root of d factor just so that everything stays within the 2D frame. And so this is a way of trying to provide you with a faithful visualization of a normal Gaussian sample in dimension d. And what do we see? Well, in dimension 2, we have nothing. Okay, this is a standard plot. So this is just a discrete equivalent of this density map. But you see that when we increase the dimension, d equals 4, d equals 9, d equals 16, 25, 100, the density concentrates around the unit ball. And this is why the intuition that you should have about high dimensional normal distributions is that they are just uniform distributions on a ball of radius sigma. Okay, when sigma is a standard deviation of your normal distribution. Okay, and this seems super strange. Okay, so yeah. So okay, so this is a strange intuition, but okay, so maybe it's a bit mind-blowing, you know, if you've been used to understanding Gaussian distributions as those bell-like shapes. throughout the last few years of your studies. But actually, it's not that surprising. And why? That's because you've already seen examples of high-dimensional Gaussian distributions, and this is what we call white noise. Okay, so white noise. So here I'm just showing to you samples of a normal distribution, completely normal distribution in dimension 100, and I'm displaying them to you as 10 by 10 images. Okay, so here, this is an image with 10 rows, 10 columns, so just 100 pixels, and every pixel value is just an independent Gaussian noise. Yeah? And we say that it's white noise because there is absolutely no correlation between the different pixel values. Okay, so this is one sample, x1. This is a second sample, x2. And what can you see? I mean, what do you immediately understand here? Well, first, none of those two samples and none of the other samples that you can imagine looks like the mean value of the distribution, which is an image which is filled with zeros. Okay, so this is exactly the equivalent of the fact that none of my high-dimensional samples looks like zero. They all look like an image that has an average norm of 1, on average, but with intensities that are that depend on the precise pixel value. Okay? So that's the first thing. The second thing is that if you take the difference between two samples, so if you take x1 minus x2, basically you recover something that looks like a white noise, but just with a bit more variance. And that's because when I computed the subtraction, x1 minus x2, what I really did was to compute at every pixel value the difference between a normal distribution of variance 1 and a normal distribution of variance 1. And you know that when you add or when you subtract two normal distributions of variance 1, you just end up with normal distribution of variance 2. So standard deviation square root of 2. So taking differences doesn't change all those statistical facts. It just increases, if you want, the amplitude of the noise. And finally, on average, all those Gaussian samples, they are orthogonal to each other. Okay, so if you take the dot product between x1 and x2, it's going to be very close to 0. I mean, at least compared to square root of d. So obviously, this is something that is only possible because we are in a high-dimensional space. Otherwise, it wouldn't be possible to fit many different samples that are all orthogonal to each other. So this is an intuition that is completely different to what you're used to in dimension 1, 2, or 3. So this fact, the fact that random Gaussian noise, or and everything I told you so far, doesn't depend on the fact that we are using Gaussian. The only hypothesis that I really made is that I assume that the columns of my data set are independent. Okay, so this fact that if you assume that you have D features, that you have more than 10 features, and that if they are independent and identically distributed, then you get this kind of behavior, is what you can call the geometric curse of dimensionality, which is complementary perspective to the statistical curse of dimensionality on overfitting that we saw just 10 minutes ago. The consequence of that is that first, because you have zero structure, you cannot do basic statistics such as histograms or density estimation, because if you want to compute histograms, you need to have many samples in a given bin, and so you need at least basically, you need an exponential number of bins to cover your space. And so conversely, you need an exponential number of samples if you want to be able to fill those bins. So the second thing is that we've seen that xi minus xj is once again something that looks like a white noise. So everything that applied to the norm of x before also applied to the norms of the differences between points. So what this means is that if I generate a large random sample D features, and D is larger than 10, then on average, the distance between xi and xj is going to be constant up to a minor fluctuation. And so it means that on average, my distance matrix is not going to contain any useful information. Basically, it's going to be a square matrix with zeros on the diagonal and a noise that is equal essentially to square root of d or square root of 2 times d plus some noise. And so we're not going to be able to do like k-nearest neighbors or kernel regression effectively. Okay, so basically the whole message here is that all of our intuitions break down. And it's impossible if you assume that you have white noise to do interesting statistics. Okay, like since everything we know breaks down, you can tell that white noise is useless from a data science perspective, like garbage in, garbage out. Like you have this, and maybe this is a naive version of the naive image that people have about machine learning is this picture. Okay, like this is your machine learning system. Yep, you pour the data into this big pile of linear algebra and collect the answers on the other side. And what if the answers are wrong? Then you just stir the pile until they start looking right. Okay, this is what people believe because they believe that we think that we are dealing with independent variables. That we are dealing with white noise. But what we know, at least what everyone knows once we've seen those pictures, is that it's never going to work. Like you cannot put a normal Gaussian prior on your data and expect anything useful if you have more than 5 or 10 columns. So what should we do? Well, usually we do implicitly or explicitly a manifold hypothesis. Basically, we assume that in this very high dimensional sample, our data is either very clustered around interesting points or that it at least lays along a space of smaller dimension. So this is a picture here that here I have a data set of 10,000 points. Naively, it looks like it's a data set with 3 features, 3 dimension x, y, z. But what you understand immediately is that we just have 2 independent degrees of freedom. Okay. And as far as histograms are concerned, as far as statistics are concerned, the dimension that matters is a dimension, like the intrinsic dimension of the data set, not the extrinsic dimension of the feature space. And so, this kind of intuition that, okay, we are dealing with high dimensional representation of our vectors, but under the hood, they are really low dimensional objects, apply to essentially all interesting classes of signal, maybe even natural images. Natural images, it looks like very complex and challenging type of data, but intuitively, you understand that natural images do not look like white noise. Usually, if you take a photo, okay, this looks like a natural image, and you don't have that many ways of changing this picture that make it still look realistic. Basically, if you have an object, maybe you can change its texture, you can change its color, you can change its position, you can change its scale. If you count all the transformation that would still let it look like a realistic image, you will end up with maybe 30 or 17 different parameters, but not, you don't have as many degrees of freedom as you have pixels. And this implicitly is what behind all the models that we do. All the models that we design, be they like convolutional neural networks or kernel methods, etc., try to capture this low dimensional structure that is behind the data. And by capturing this low dimensional structure, enable interesting statistics. So that's the spirit in which I designed the class. Try to give you elements of vocabulary, intuitions to work with these notions. And so what is coming next, in the next few lectures? So you understand that if you have this type of object, you can either try to describe it discretely using a graph, like a graph of k-nearest neighbors, or you can try to describe it continuously as a surface. And both points of view are valid. So when I first designed the class, I thought, okay, I'm going to do, as in every good mathematical lecture, I'm going to start with a continuous thing, because usually this was the way ideas were developed in mathematics in the 19th century. People started by doing continuous objects and then went on to study discrete objects, etc. But okay, I realized that no, this is completely counterintuitive. So I will first talk about discrete descriptions, so graphs. This is today. Then next week, we're going to talk about doing deep learning like advanced methods on those graphs and point clouds, see how far we can go and see that actually maybe it's interesting, but not as much as you hope that it is. And then in lecture 5, we're going to study the same objects, so balls, hyperbolic manifolds, etc., but from a continuous perspective. I'm going to introduce to you the vocabulary of manifold geodesics. And in lecture 6, study a type of manifold which is extremely relevant to data science and machine learning, which are statistical manifolds, so spaces of probability distributions, endowed with like the relative entropy or the Wasserstein distance. So that's really going to be the core of the class. And finally, in lecture 7, last but not least, I'm going to talk about the hardware bottlenecks, like the software, the implementation issues that force us to study some kind of algorithmic structures over other one. Okay, that's because even though it's not theoretical mathematics or pure geometry, it's very important to understand the computers that we have to understand where the research is heading. Okay, because at the end of the day, we are interested in methods that are scalable. So, but that's kind of an exception. And so at least for the next 4 lectures, the aim of the class is going to let you bridge a gap between those discrete and continuous descriptions of the underlying problem structures. So today's lecture, first, we're going to take maybe 30 minutes to say why we care about graphs. And then once we have understood what's a graph and what is not a graph, like basically we are going to understand that graphs are really not easy to work with at all. We are going to talk about local descriptors and archetypes that can provide us with some intuition about those metric spaces. So we're going to talk about dimension and curvature and see, okay, what are the ideal metric spaces that people think about when researchers talk about graphs. So then we are going to make a break, and then we're going to make a real workshop session for once about embedding tools, okay, that allow us to go from a local graph description to a global 2D visualization, and so allow us to try to get a global intuition on the object that we deal with. Okay, and so we could have studied like the most simple embedding methods like spectral embeddings, isomap, t-SNE, etc. But I want to focus directly on essentially one of the state-of-the-art methods, which is extremely well packaged, which is UMAP. Okay, so I know if you've already used that, but it's really worth knowing about. So that's it for today. And so I don't know if you have questions, maybe. Yeah, sorry, because I was a bit distracted by all those problems with the Wi-Fi. I'm really sorry that it didn't work. Okay, so now let's move on to what you came up for, which is graphs. Okay, so why do we care about graphs? Maybe a first motivation to care about graphs is that it's a type of structure that very often comes up when you talk with domain experts. Okay, let's assume that once again, we're having a cake with doctors, and you're asking them like, okay, you gave me this table, but I don't understand the features. I don't understand the columns. Because for every patient, you gave me 20 or 50 different measurements. And me, as a mathematician, I don't understand what I'm seeing. And maybe they're going to tell you, oh, we don't know either. We do not fully understand the columns of our table. But instead, we can definitely tell you that this patient A is similar to patient B. Okay? Maybe instead of describing patients as vectors in a space that we do not completely understand, they are more comfortable describing them as nodes in a space and drawing explicit edges between them. So they have this picture of the space of patients, or at least implicitly, where this is patient 1, this is patient 2, 3, 4, 5, 6, and they're able to give you this list of patients. Maybe you have features on those patients, and alongside this list of patients, a list of edges. I'll tell you, okay, this is close to this one. Okay, so this definition of graph is the algorithmic definition, probably the one you're most familiar with. Say that a graph is just a discrete collection of vertices and edges. From a geometric perspective, if we didn't care about computers, we could think instead of graphs as metric spaces that are defined locally. If a graph it's a distance, but which is only given to you for small values. So you know that the distance between patient 1 and 2 is 1, patient 2 and 5 is 1, patient 5 and 1 is 1. You know that distance between patient 2 and 3 is 1, also 3, 4, also 4, 6. And then the whole challenge is to try to go from this local definition to a global distance. Try to take a higher view and go from there and understand that maybe the distance between patient 1 and 6 is around 3. Okay, maybe compute geodesic things, etc. Geodesic distances. So, okay, so that's the first motivation, but you have many other motivations, in computer science to study graphs. First is that physical graphs do exist, okay, in real life. You think about transportation networks, like the RER or metro network, and historically, most importantly, communication and power lines. That all the study in computer science about information geometry, information theory, and graphs was motivated by the needs of like Bell Labs or in France Orange, France Telecom. Basically, the need to send information packets, so either audio communication or today internet bytes from one place to the other, and we have a physical network where we have data centers, data hubs, and physical lines that join them together. So, okay. So sometimes this description is actually the one that you have in the physical world. Also, a second good motivation, at least for me, is that graphs come up very often when you work with 3D data, 3D anatomy. So here I'm showing you two different anatomical structures. First, a vascular network. So this is an image of the arteries inside the brain. Okay, so here, basically the eyes are around here, and this is the back of the head. And when you have such a vascular network, you can think of it maybe as a point cloud. But if you think of it purely as a point cloud, then you're going to believe that, for instance, the distance between this point and this point is very small, because in 3D space, they are close together. But for most applications, this is not really relevant, especially for surgery. If someone has a stroke and you need to operate them quickly, what really matters is the distance between them along the network. And so to understand this intrinsic distance along the network of blood vessels, you need to define a graph and be interested more in the intrinsic geodesic distance than about the extrinsic 3D distance that comes from the embedding. So first motivation, just like 1D graph, and also anatomical surfaces are important too. Okay, so this is a brain surface, but not the surface between the gray matter and the outside and the outside fluid, but between the white matter and the gray matter. Okay. So this is a place in the brain where the cortex cells kind of interact with all those cables that make up the white matter. And here, once again, you could just say that, okay, this is a 3D-point cloud and this point is close to this one. But if you talk to neurologists, they are going to tell you that no, the distance that matters is the distance along the surface. Like if you want to segment the brain into meaningful anatomical regions, you have to take this distance into account. And so you have to think of this object more as a graph than as a 3D-point cloud embedded in R3. So like those are all real graphs. And finally, even if you're just working with very high dimensional samples, you have a simple way of getting a graph out of it. And that to build a graph of k nearest neighbors. So here, I'm displaying, once again, this kind of Swiss roll data set. So this very idealistic idea of a 2D data set embedded in 3D space. And all the black segments, are just edges that pop up when I connect each point to its k nearest neighbors. So here I think k is equal to like 5. Okay? And the idea behind many graph methods, especially for the study of 3D point clouds and some data sets in biology, is that if our data has low dimensional structure, then this should be visible on this neighborhood structure. And this graph structure should be kind of invariant to the way that our 2D surface was folded in 3D space, and so we should be able to recover it. So maybe one last thing that I want to insist on is that you don't have to think of graphs as discrete objects, with either there is an edge or there is none. You can also think as a graph as a connectivity matrix. So here, let's assume that I have 8 points, that I compute distances between my points, and then I apply a threshold. So this is kind of applying this kind of step function on the distance. This allows me to recover a discrete connectivity matrix, okay? Where here I say that this point is only connected to himself, while this point, point 2, is connected to itself, as well as point 6 and point 8. So this is ball tree, very simple, analogous to K-line graph. And even though we could work with this sparse connectivity matrix, we could also decide to work with a smoother kernel matrix, the kind of object that we saw last week. And this is just the object that pops up when, instead of applying a discrete threshold on a distance matrix, I apply a soft threshold function. And maybe this is more computationally expensive, even though, as we're going to see at the end of the lecture, it's not always the case. Sometimes it's actually much more efficient to work with this matrix than with this one. But most importantly, the advantage of this method is that you do not have this sharp cutoff anymore. And so if you want to design smooth decision rules, things that are a bit more robust, probably this is a good idea. Okay. So that's about graphs, and the spirit in which we're going to study them is try not to do as classical geometers. I think I'm sure that you've already had lectures about graph theory, and probably your lecture started with this picture, the picture of the Königsberg bridges, this kind of toy problems in what is now Russia, not Poland, Russia, about the city where people wanted to do a nice walk by going on every, walking through every bridge once, and people tell you that, okay, this is how Euler kind of came up with the idea of summarizing things and working with graph theory. And usually we are told that this is very different to the study of continuous surfaces, like complex geometry, etc. And maybe this is how people thought about it in the 19th century, even though arguably they didn't put such a strong barrier between the two. But at least since the 1980s, mathematicians don't think about this object this way anymore. Okay. Massive ideas that came up, especially with people like Mikhail Gromov in the 1980s, were to understand that graphs and continuous surfaces manifold share similar properties, and that we should strive to define notion of curvature, dimension, that work in both settings. And so in some sense, and in 3 weeks it's going to be clear for you, a tree, a discrete graph structure, is very similar, has a lot of similarities with a salad, like a hyperbolic salad. Okay, and this is the kind of ideas that hopefully will be clear for you soon and allow you to develop intuitions about graphs. So, I've tried to push the point home a bit heavily, but in all of this subject, okay, it's not the encoding that matters, but the geometry that is inside. Here I have several descriptions of, I think it's a Faust data set, so just people moving around. Okay. And what you see is that, for instance, this mesh and this mesh do not have similar triangulations. Maybe this triangulation has zones with different sampling densities, where this mesh is more homogeneous. Maybe this is a low resolution mesh, where this is a high resolution mesh, and these are point clouds. And I think that many people in our field, in data science, machine learning, since they come from computer science and they have not been exposed to these pictures about metric spaces, they tend to think of these objects as very distinct from each other. And you immediately see that it's not optimal. Okay. Instead, you should think of this object just as different projections of a continuous geometry. And this projection should not distract you from what matters, which is the actual 3D geometry. And hopefully, once you have understood that all these objects are just different representations of the same thing, then you will be able to pick the representation that is best suited to your purposes, because obviously they have very different numerical properties. Right? As far as the computer is concerned, this is very different to this. But as far as we as humans are concerned, these are the same things. So, having said all of that, a bit of a motivational thing, real life graph science is much harder than that. Okay, and why is that so? That's because when you get a graph, usually you just get two massive arrays. Okay, one array of vertices, one array of edges, and it's very hard to entangle it. So it's a bit as though you were in front of a dish of spaghetti or a web full of nuts. And a mathematician tells you, yes, the curvature here, it's very interesting and all that. But it's highly non-trivial to go from this very local description where you know that this point is connected to this one to a high-dimensional picture. And this you could argue this is the main open challenge in geometry. How do we go from a local connectivity or from a local Riemannian metric to a global structure? And it's very open. There is no magic toolbox, and so I'm not going to tell you that graph machine learning is a solved problem by any means. Okay, so the only thing I can give you this week and the week after are just some intuitions, some examples of tools that have been developed 20 years or 2 years ago, and hope for the best, and maybe hope that it will give you ideas for your future work. So also graph machine learning is hard, both because computationally it's not nearly as easy as machine learning on images or signals, but also because it's a very wide topic. People think that if they have a graph, they have said something. But as we've seen, when you say that you have a graph, you just say, I have a metric space. And this is very vague. Okay, and you cannot hope to have a silver bullet to tackle all those problems differently. So currently, I think the spirit in research is more try to classify the different types of graph, or try to classify the different parts of a graph into maybe easy regions, bottleneck regions, etc. And this is a kind of understanding that is emerging and that I'm trying to convey to you. So that's about the spirit. And so maybe we can start with just talking about dimension. That's the most simple thing. Is your graph a metric space more of dimension 1 or dimension 2 or dimension 3? So what is dimension? The simple definition is to say this is a number of degrees of freedom. And we are used to that in our daily lives because it's a vocabulary which is completely ubiquitous in the video game industry. Okay, we know that Pong is a 1D game. You can just go up and down. Pac-Man is a 2D game. And Minecraft is a 3D game because you can go up in front, on the side, and you can go below the ground. So for geometric objects, at least simple geometric objects, it's the same story. A segment is a one-dimensional object. A disk clearly is two-dimensional, and a bulb clearly is three-dimensional. What about real-life graphs? Well, a first answer is that if your graph comes from a sample point cloud, a 2D point cloud, a 3D point cloud, or a high-dimensional point cloud, then answering the question can be very easy. And why is that so? That's because if you have a graph with coordinates, like if your points have x, y coordinates, then it's very easy to fit locally an ellipsoid to your data set. How do you do that? Okay, so first you have your point cloud, then you compute your k nearest neighbors graph, or your radius ball graph. So you say that, okay, this point is connected to this one, this point connected to those two, this point connected to those 5 other ones. And then, so for every vertex, you have a small sub data set of points that are in the neighborhood. And what you can do easily is to fit an ellipsoid to this local neighborhood, to this local context, shape context. This is exactly what PCA is about. So, by the way, because I'm talking about PCA, but I don't know how clear the technique is for you. Like, is it totally obvious what PCA is or not really? No, oh, not really. Okay. Sorry. Okay, no, it's good that you tell me. Okay, so maybe I don't know if you've ever seen covariance matrices or never. So the algebraic definition of PCA that people will tell you is that PCA is about computing for every point the local covariance matrix. And you have, so for every point, you end up here with a 2x2 covariance matrix, and then they tell you, oh, you should diagonalize it, and you're going to get principal angles, principal lengths, and so this allows you to understand the main modes of variation of your data. Okay, but this is an algebraic definition. I think it's not so clear. The geometric definition of PCA is that you have a local data set, or you have a data set, and you try to fit a Gaussian distribution to your data set. So here you imagine that this point only looks at itself, its first neighbor, and its second neighbor. So you have a dummy data set with 3 points, and you try to fit a Gaussian distribution to it. And then what is the kind of most likely Gaussian distribution to explain this type of data? Well, it's going to be a multivariate normal distribution that looks like this. A kind of tilted Gaussian distribution, because if I had, so I try to fit a normal distribution, but that is not necessarily isotropic, otherwise it would be trivial, but I allow myself any kind of covariance matrix. And so, and this simple process geometrically allows you to fit a local ellipsoid to a point distribution. Yeah? And at the end of the day, this is what PCA gives you. Okay, PCA, if you principal component analysis, if you don't like all the stories about eigenvalues, etc., because it heavily depends on your background, PCA is about taking a point cloud, fitting an ellipsoid, and then returning to you a collection of vectors that describes the main axis of variation and a collection of lengths. So a first length that tell you, okay, in this first direction, you have a big variation, and the second length here that tells you that in the second direction, you have small variation. So, and the good thing about PCA is that it's very easy to compute on a computer numerically. So you can just think of it as a magical routine that fits the small ellipsoid to neighborhoods. And so here, yeah.
When I've heard about PCA, I was applying it to the entire data set,
yes.
To 3 points.
Yes.
And this is the part I don't understand why you would apply PCA on this.
Yes. Okay, so the thing here is that intuitively, you understand that this looks more like a 1D object, and this looks more like a 2D object. Okay, and if I apply PCA to the full data set, I would observe an ellipsoid that looks like this, kind of a big ellipsoid, and I would say that everything is 2D. But then I would never be, so it would work if I was just interested in the global dimension of my data set. But here you see, in the spirit of trying to understand the local dimension of the data, about the manifold, basically, if I apply this methodology to a Swiss roll data set, I'm just going to get a big 3D ball. I'm never going to end up with this number of 2, this magical number of 2. And so what we try to do by restricting the field of view, and so building a collection of small subsets, is to give a chance to PCA to highlight the local dimension of the data set. Okay, and so this is what happens here, because here, when you're right in the middle of the 2D region, then you observe an isotropic variation. So we get a 2D disk. So this is clearly 2D. But here, we observe something that is very anisotropic, and so we can hope to say that this is one-dimensional. So I don't know if it's a bit clear for you. Yeah.
And how do you decide how many points one fit on?
So yeah, okay. So this is really up to you. So but this will come up in visualizations. Usually, what you do is you use the type of toolbox that we're going to use in the lab session, so UMAP. You get a visualization, and then for every point, you compute a k-nearest neighbors graph, you compute this kind of dimension, and you see how smooth it is. And if it varies everywhere, you say, okay, clearly this is too noisy, so you're going to try to increase the number k until it smooth things out. Okay. I mean, all of these are just heuristics. It's nothing super rigorous, just a way of trying to make sense of what we have. So, okay, so basically, using those numerical routines, you're able to fit locally an ellipsoid. And then the good thing is that you can try now to answer the question, what is the dimension of an ellipsoid? So clearly, an ellipsoid which is degenerate, like just one non-zero direction and one zero direction, clearly has dimension 1, like it corresponds to a region of dimension 1. An ellipsoid that has two great axes of equal length, so a circle, a disk, clearly is of dimension 2. But then in real life, most of the time, you're going to observe something in between. Just because you have noise in your data, even on the Swiss roll data set, you're never going to observe a completely planar covariance matrix. You're always going to have a bit of depth. And so now you have to make a choice, okay? Given an ellipsoid, what you know thanks to PCA is a collection of lengths of the principal axes. So you have length 1, length 2. So here, length 1 is equal to 1, length 2 is equal to 0. Here, length 1 is equal to 1, length 2 is equal to like 0.3. And here, length 1 is equal to 1, length 2 is equal to 1. So you have just this vector of lengths. You can square them, okay, to get the diagonal coefficients of the PCA. You can normalize them just to be a bit small scale invariant. So you get those coefficients Li, like so lambda I squared divided by the sum. So super easy to compute if you have access to PCA. And then you have to use a rule of thumb to say that this is more one-dimensional, this is more two-dimensional. So a typical rule of thumb, which is the one which is used by UMAP, is to say that the local dimension D at a given location is what you get when you fit a PCA. You compute those coefficients, and we take the small index D, such that L1 plus L2 plus L3 plus LD explains more than 80% of the total variance. So you can take total volume of the ellipsoid. So just a simple convention where you kind of apply a threshold. You say that, okay, this is clearly dimension 1, this is clearly dimension 2. But here, essentially, so if it's very thin, it's dimension 1. If it goes beyond some threshold, it's going to be dimension 2. So this rule gives you an integer dimension, but obviously using some kind of rational fraction of the LIs, you're also able to define formulas that interpolate smoothly between dimension 1, dimension 2, that work well in any dimension, etc. Okay. So just to tell you that at least for data sets that come from a point cloud, for graphs that come from a point cloud, it's kind of easy to define good heuristics. But then, what about pure graphs? Okay, because those objects are also interesting. Think of a network of a power network or of the internet network, and there you don't have local coordinates, so you cannot really do those PCAs. And so instead, an idea that also comes from fundamental mathematics is to try to compute a kind of Hausdorff dimension. So look at the volume of balls of radius r. So here I have I have a graph. Clearly, it's a two-dimensional grid, and a ball centered around x of radius 0 contains just one node. A ball centered around x of radius 1 contains 5 nodes. A ball centered around x of radius 2 contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, and then ball of radius 3. And what's interesting is that at least for those kind of grids, we can show that the volume of this ball of radius r grows polynomially with the radius on simple spaces. And so you could define the dimension as a degree of this polynomial. So in other words, okay, d will be the integer or the number, the real number, such that the volume of a ball centered around x of radius r grows like r to the power d. And so, if you apply the logarithm, yes. Yes, totally. So here, okay, so just to be clear, when I'm talking about volume, actually it's just a number of nodes. And the ball, the ball is purely defined on the graph, through the geodetic distance. So we don't need XY features. So yes. Yes. Also. Yes. Yeah. Oh, okay. Yes. Because you assume that you want a definition which is robust to the concatenation of two graphs, and so maybe if you concatenate a curve with a surface, you want a definition which says that on the curve it's dimension 1, on the surface it's dimension 2. So, and that's the Hausdorff dimension. And the way you would estimate this numerically is to say, okay, you would compute the volume of the ball of radius r for r, which is equal to 1, 2, 3, 4, 5. You would apply a logarithm, and then you would divide this by the logarithm of r and try to find a good value. So in other words, you would try to find d would be the linear regression coefficient between the logarithm of r and the logarithm of the volume of the ball centered around x of radius r. So this looks like a good idea, and it's a definition that definitely works for many objects that come from classical geometry. So probably maybe you've heard about that under the name of fractal dimension, because it's a dimension that you can apply to things like a Sierpinski triangle, etc. So just to be clear, here I have an object. Let's say that this is kind of radius 1. And what happens if I go from radius 1 to radius 2? Here on this clearly 2D object, the volume of my ball goes from 1 to 1, 2, 3, 4. So on average, if you take this formula, where you take the log of the volume of a ball divided by the log of the radius, here you have a logarithm of 4 divided by a logarithm of 2. And so the dimension is, log 4 is just 2 times the logarithm of 2. So it's dimension 2. Okay, so this just expresses the fact that on a 2D plane, when you double the radius of an object, you multiply its volume by 4. And obviously, on a 2D surface, volumes means area. On a 3D object, you have 3 degrees of freedom. And now, when you take a small cube and you multiply its length by 2, you multiply the volume by 8. And so in those formula, you find 8 copies of the same subgraph. So you have logarithm of 8 divided by logarithm of 2, so it's 3. And for fractal objects, like the Sierpinski triangle, here you had a small triangle, you multiply the edge length by 2, and you retrieve 3 copies of the same object. So that's why we said that this object has dimension logarithm of 3 divided by logarithm of 2. And that's why we said that the Sierpinski triangle is an object that has a non-integer dimension. Okay, so this is all like the type of thing that you would learn in a course of classical geometry. But the problem is that for graphs, it doesn't work so well. And why is that so? So maybe, so I understand that, okay, it's a bit complicated, if you don't know about it, but, I just showed it to you to tell you that there are good reasons to think that this is a good definition. It's just that for our purposes, it's not going to cut it. Okay. So, okay, and why is that so? That's because on a general graph, this volume function is not always a polynomial function of R. And for this, I can try to give you archetypal examples. First, think about a clique. A network where you have lots of connection between the different nodes. Then, okay, if you take, for instance, this node, then a ball centered around x of radius 0 is just 1. And a ball centered on x of radius 1, it's already immediately the full graph. So there is nothing to, the volume of the ball plateaus very quickly. There is nothing to make regression on. An archetypal example of a graph where this happens is in a social community. Probably you've heard about the fact that if you go on Facebook, or basically if you try to connect with the friends of friends of friends of friends, you can connect with anyone on Earth, or anyone, let's say, in the Western world, with just five steps. So arguably, in those kind of networks, the diameter is so small that you do not gain anything by computing those kind of quantities. So, okay, so this is an important example where clearly the half dimension doesn't make sense. Then you have an example which is grids, okay, 2 degrees, 3 degrees, and in this example, the definition makes sense. Okay, and that's not a surprise because this is exactly what we had in mind when we defined the Hausdorff dimension. So that's a good thing. But then a third class of graph, or very interesting graph, is a class of trees. Okay, and if you think about it, on a tree, the volume of a ball grows exponentially fast. Okay? Because at every time you increase the radius of a ball on a tree by 1, you multiply the number of nodes here by 4. Okay, so you have an exponential function, not a polynomial. And so if you try to apply this linear regression, you do not get a useful coefficient. So we see that, so we understand that, okay, defining a notion of dimension on a graph is going to be harder than we thought. And actually, this type of situation reminds us of classical examples from continuous geometry. So notably, I think this one, you can understand it, even if you didn't have background in geometry, is that think about a sphere, a small sphere. You have a point, and you're interested in the area of a ball of radius r on the sphere. You see that maybe at first the area of this disk grows like a polynomial of degree 2, but very quickly you feel the whole sphere. It is very small. So in some sense, you understand that there is an analogy between a sphere and this type of graph. And so actually, it's not a coincidence that when you try to display cliques as aesthetically pleasing graphs, you display them using ball-like shapes. Okay, so then you have Euclidean planes, so this is like this, and those kind of exponential behaviors of the volume function remind people of hyperbolic spaces like the Poincaré disk. Okay, so notions that we're going to see in 2 weeks, but I had to make a switch between either first showing you discrete objects like trees or continuous objects like Poincaré disk, and I thought, okay, showing you first trees is easier. So we're going to start with that. Okay, so those analogies led people to believe that maybe dimension on a graph is not so well defined, and so instead we should try to understand curvature. And why curvature? Because basically the main difference between a plane and a ball is that the ball has high curvature, and this is what makes the volume function not polynomial. Okay. So here we are. So maybe we can do a small break because I think, I gave you a lot of information. Yeah, so try to refresh a little bit. Then we are going to talk not so much about curvature, I'm just going to give you a few intuitions, and then we're going to be back to we're going to make a lab sessions. That should be easy. Okay. Okay. So we're back for just 30 minutes of a little bit of intuition on curvature before making a lab session and hopefully making it a bit more concrete. Okay, so maybe just a word about the construction of this session and the session after. Okay, so as I've told you, the main objective of the class is to introduce to you the tools and the vocabulary that people think about when they think about manifolds and graphs, metric spaces that are not Euclidean. And the thing about manifolds and like probability distributions, so the last 3 classes, is that they are very well understood. Like there are still many interesting open problems, but as a rule, I'm just checking that I'm saving. But as a rule, basically, we know what are the concepts that are extremely relevant and that should be taught to graduate students. The problem with graphs is that the picture is not nearly as clear as it is for probability distributions. Okay, you have, let's say, historic tools that have been developed for telecommunication networks, but that are completely irrelevant for instance, 3D meshes. On the other hand, you have lots of intuition that have been developed on 3D meshes that are not at all relevant for social networks, those kind of things. And intrinsically, this comes from the fact that a graph is a very ill-defined object, or let's say it's a very vague object. And so what I'm trying to do today is to convey you some of the most basic intuitions that researchers have on those objects, so dimension, curvature. And then in the next session, we're going to talk a little bit about, how people try to design complex models on graphs. And we're going to see that sometimes it works, sometimes it's just very unclear as of 2022 when you look at the literature, what is important and what is not. Okay. And so that's why we are making this kind of overview with lots of intuitions. And I understand that probably you want to dig a little bit deeper. Okay, if some of the notions catch your eye, or if you want to understand what is happening. And so for this, I can suggest, if you want to read textbooks on the subject, I can suggest 3 ways of doing that. The first one is you can go on my webpage, the webpage of the class, and there is a paragraph when I say, okay, this is where you have access to the slides, this is where you have access to the videos. And at the end, I have included some links to interesting textbooks. Okay, so definitely have a look at them, because this is just an introductory class, which is supposed to be like a kind of gateway drug for the geometry lectures of the second semester. Second option is just download the slides and, and click on the links. Click on the links. They are going to take, for instance, this picture. I tell you where I took it from. And this is a paper from like France in London. It was published like 2 years ago. And you can read the references and understand where people are coming from when they display those toy examples in very recent research papers. Okay. And finally, obviously, you can just look at the list of projects, because all the papers that I listed as projects, I think, are very interesting ideas. And as you can see, especially in the section about graphs, it's very diverse. You have lots of very different ideas. Okay. So what is really going to be worth teaching in 10 years, we don't really know. Okay. So, but that's the reality of a research master. Okay. So what we've seen first is that due to the cost of dimensionality, you cannot expect to do great things with white noise. Second, that sometimes you'd like to understand the lower dimensional data space of plausible data samples through a graph structure. And we've seen that even though the notion of dimension is appealing, and even though it can be applied to some graphs, like 3D point cloud and some other types of graph. Like you can, as a rule of thumb, say that this is more dimension 5, this is more dimension 10. It's not a notion which is very precise, and it's a notion that breaks down even on very common types of graphs like cliques and trees. Okay, and in our current research work, in our attempt to understand what on earth is happening, like how can we describe, how can we put a vocabulary on these trees, on these structures, that people have tried to define notions of curvature on graphs, because intuitively the notion of curvature should allow us at least to distinguish between those three archetypal families of graphs. Because as we're going to see, this is more like positive curvature, this is flat curvature, and this is negative curvature. So, okay, so, but where does this come from? So just as a question, like, could you raise your hand if you've ever been introduced to the notion of curvature in 1D or 2D? Okay, so not really. Okay, that's interesting. Okay, because back in my days, in prepa, at least we're doing these kind of things on curves. Okay, like the curvature of a curve. What is that? So assume that you have a one-dimensional curve on the plane. You know that you have the position and you have the tangent. Okay, the derivative. Okay, this is easy, but then you can also define an order 2 approximation. Try to go beyond the description of order 1, and the order 2 approximation, like in your Taylor expansion of your curve, is going to allow you to fit a circle. Okay, it's called the osculating circle. And curvature is just defined as the inverse of the radius of this circle that best fits your curve. So for instance, for a planar curve, like a straight line, is best understood as a circle of infinite radius. So 1 divided by plus infinity, it's 0. So a straight line is curvature 0. But here, you have this kind of curve, so it's best approximated by this circle. And so you have a fairly low curvature, whereas here, a curve that does a lot of wiggles is best approximated by a small circle. And so we say that it has a high curvature. So this is how you define curvature for a 1D curve. Now, what about 2D surfaces? Well, on a 2D surface, you can draw curves. You can draw straight lines, that we call geodesics. And so a way of defining curvature on a 2D surface is to say, okay, I pick a direction, I draw the straight line. So think on the plane, a straight line, on a sphere, a great circle, and I compute just the curvature of this one-dimensional curve. And you do that for all directions, like you turn around 360 degrees. And what you will find, it's fairly easy to show, is that you have two orthogonal directions where you have minimal and maximal curvature. And these two directions, we call, and the two curvatures that are associated to those directions, we call them the principal curvatures. And we call the value of the curvature, the largest curvature, we call this kappa 1, and the smallest curvature, we call this kappa 2. Okay, so this is the abstract definition, but let's look at basic examples. So first, a plane. On a plane, all the geodesics are straight lines, and so the value of the curvature does not depend on the direction. So the value of the curvature with respect to the angle, it's a constant function. And so you have kappa 1 equal kappa 2 equals 0. It's very flat. Now, you look at this type of surface, slightly curved. Here, you have that in both directions, like in all directions, you observe something which is curved like this. And so we say that kappa 1, kappa 2 are positive, but not too large. Whereas here, for a surface which is more curvy, I mean, this is where the name comes from, basically the radius of the circle that approximates this type of thing is smaller, and so the curvature is higher. In terms of Taylor expansions, the curvature, you can understand it as the coefficient of the Hessians. Okay, so here, you have no Hessian, so the curvature is 0. here, it's like a polynomial of degree 2, but with a small factor in front of x squared. So the curvature is small. And here, it's like 10 times x squared. So you have a big coefficient. So that's for simple options. And then you have 3 archetypal examples. First, you have the sphere. Okay, a sphere is characterized by the fact that on every point, in any direction, the curvature is always constant, and it's equal to 1 divided by the radius of the sphere. Because remember that the curvature is defined through the base sphere that approximates geodesics. And it makes sense that we recover this value. Then you think about a cylinder, a tube. You have one direction in which the geodesics are straight. And so in one direction, you have curvature 0. And in the other direction, you have something that is a circle, so with positive curvature. And finally, you look at those kind of, we call those hyperbolic surfaces, where in one direction, you have positive curvature in one direction, and in the other direction, you have also curvature, but in the other direction. And so we orient the curvatures according to the normals, and so we say that we have 2 non-zero values, but of opposite signs. Okay, and the convention is to say that the sign of the curvature of the surface is given by the product of the 2 curvatures. So when we say that the surface has positive curvature, what you really mean is that kappa 1 times kappa 2 is positive. Okay, and this is the case here. Kappa 1 times kappa 2 is 1 over r times 1 over r squared. Well, so it's positive. Here, kappa 1 times kappa 2 is equal to 0, because it's positive times 0. And so we say that the curvature, the Gauss curvature of this surface is 0. So in a sense, it's flat. It's a flat surface that has been folded in 3D space. And here, because the curvatures are in opposite directions, we say that they have opposite signs, and so kappa 1 times kappa 2 is negative. Okay, so this is an archetypal image. Now, this notion has a long history. You probably know that, okay, this is how we describe space-time, like general relativity tells us that we live in a curved 4-dimensional space. Okay, so it's a subject that has been studied to death, okay, over the last 200 years. But without going to those not strange, but complex physical theories, we can immediately see that curvature has direct uses in physics and biology. It's a very useful descriptor of the surface of a shape. For instance, let's look at what we call the plateau problem. So trying to understand the surface of soap bubbles. Actually, if you do the math or if you do basic physics modeling, you see that a soap bubble tries to minimize the area, so the integral of the area of just a constant, under some constraints. So here, the constraint is that this is a closed surface, and but that encloses a finite volume which is fixed. So actually, we can show, it's called the isoperimetric problem. We can show that this sphere is what minimizes the area, subject to a constraint that the volume is the volume of this bubble. So this is one thing, but we can add different other types of constraints, and so and for instance, this is what happens, when you take a wire, you put it in soap water, and you're able, to get those type of surfaces, and those surfaces are exactly what you get when you try to minimize the area of a sphere with a constraint that your surface should have the boundary which is equal to the 3D positions of your wires. Okay, and what's interesting, if you do the math, is that for those 2 cases, like those open surfaces, you can show that the minimal surface, the shape that actually occurs in nature, is such that kappa 1 plus kappa 2 is equal to 0. We say that the mean curvature, so the sum of the 2 curvature, is equal to 0. So here, basically this picture is exactly what we had here. We have a direction of positive curvature and a direction of negative curvature, and at every location, they both compensate. And this is because at a physical level, the force that is that is applied by all the neighboring points is exactly proportional to the mean curvature. So that's one thing, but this maybe you already knew about it. If you go to La Villette in the Palais des Sciences, they explain this to you, but we can go further than that. For instance, we can show. Yeah.
Isn't that false for the bowl?
Yes, exactly. Exactly. That's why I said this and this. So the thing is that, so that's what we call minimal surfaces. They minimize this area. And so we can say that in the space of surfaces, minimal surfaces are critical points of this energy. But the thing here is that you have the constraint of volume that leads to a different equation. Whereas here, basically, you don't have a constraint of volume, just a constraint about the wires. And so in a sense, the particles of soap, of water and soap here are more free. So basically here, this particle of soap, the only forces that are exerted on it are the weight, but this is negligible, and the surface tension. Whereas here, you have the surface tension and you also have the pressure of the air or something. So exactly. So more interestingly, maybe a bit mind-blowing, is that red blood cells, they also minimize an energy that has a similar form. It's called the Helfrich energy. So this shape that you know is exactly what you get when you try to minimize under a constant volume constraint an energy which is the integral of the surface of h minus h0 squared. So you prescribe a non-zero mean curvature, and you try to have a surface that at every point has a mean curvature which is roughly equal to h0. So this is like this model already out of the box allows you to describe the shape of red blood cell. And what's interesting is that if you complexify the model a little bit, like you add extra terms, you get those types of shapes, and these shapes actually occur in nature. They are associated to some kind of diseases or whatever. Going even further, instead of just looking at kappa 1 plus kappa 2 minus h0, we can try to minimize arbitrary polynomials of the curvatures. So we may be interested in surfaces that minimize the integral of a surface under a constant volume area of something, a polynomial of degree 2. You have a coefficients for kappa 1 squared, coefficients for kappa 1, kappa 2, a coefficient for kappa 2 squared, kappa 1, kappa 2, and a constant term. And the cool thing is that if you plot the results for different polynomials of kappa 1 and kappa 2, you get shapes that naturally occur in biology. So maybe you get collection of droplets, you get tubes, you get other tubes, and you get membranes. So, when you look at this picture, you understand that curvature, at least in the 3D world, looks like a powerful descriptor. Like just using this model with different polynomial, we're able to generate surfaces that look like a microscopic image of aluminum foam. Here, this is lamina fibrosa. So that's essentially a piece of collagen that is right at the location in your eye where the optic nerve connects to the retina. Here, this looks like essentially the inside of your bones in the bone marrow. This looks like another polymer form, and this looks like the endoplasmic reticulum that we have in our cells. So, like for me, very surprising to see that just with a simple polynomial, we're able first to simulate red blood cells and then to simulate forms in biology. So it definitely captures something interesting. And as a side note, I would like to stress that those images were generated by people who come from the MVA. Okay, so just to tell you that your skill set goes way beyond doing deep learning research. And I think I have to tell you this because I gave you a long list of projects, and it looks like 90% of you went straight to graph neural networks. Okay, and I understand it looks fun and all that. But I mean, you have all those other topics on 3D geometry, shape spaces, probability distribution, which to me are just as cool. And basically, it's the same community of research. That people, sometimes they publish 3D papers, sometimes on graphs, but usually they go in between the fields. So that's one thing. And second, like you can use use your knowledge about GPU processing to implement, biological models. You don't have to do hyperparameter tuning if you don't want to. So why I tell you that? That because how did we, generate those images? How did we generate those surfaces that have very complex topology that minimize an integral of a strange polynomial of the curvature? Actually, the people who wrote this paper, they did some math and they were able to reformulate an energy on surface into an energy on volumes, where the volume is like the indicator function of I am inside the vessels. It's called a phase field expansion, and it's fairly common in physics to do this kind of math. So basically, you're able to express your surface energy as a volumetric loss function. Actually, if you do the math, you realize that it's a convolutional energy. So the way, given a volume, the way you express this energy is you apply some convolutions. You can do it using PyTorch. Then you apply some nonlinearities, some polynomials. And then you integrate it, and it's a 3D equivalent of the 2D energy. So it's a bit of a statistical descriptor of the texture that you can optimize, just like we optimized 2 weeks ago the texture of paintings, with a cat. So those images, they were generated exactly as the cat pictures that I showed you 2 weeks ago. Essentially, the authors, they started with white noise, which is common if you want to do texture generation. And then using gradient descent, they minimize their 3D phase field energy, implemented on GPU with PyTorch. So this type of model combines math, GPU computing, imaging data. It fits perfectly within your skill set. And it's the kind of research that people who do geometric deep learning like to read. It gives inspiration. So it's completely a continuum of research. So just to tell you that, especially if you do a PhD in deep learning, I would advise you not to spend your whole PhD just reading papers of people who tune hyperparameters. You try to write in your research because it gives you super interesting ideas. So basically, all of this is super motivating to try to define curvature on graphs. But can we really do it? Because curvature seems to be a very continuous object. We are taking derivatives of curves in 3D space, so it looks strange. And actually, there is a very famous theorem by Gauss, 200 years old theorem, that tells us that some curvature can be defined on graphs, some curvatures cannot. And on 2D surfaces, it's called the theorem egregium. Basically, you have your surface, you have kappa 1, kappa 2, and we can show that the sum of kappa 1 and kappa 2 is completely extrinsic. Like it's something that depends on the embedding of your surface in 3D space. So for instance, if you take a sheet of paper, kappa 1 equals 0, kappa 2 equals 0. But then if you fold this sheet of paper without tearing it or anything, just you fold it, you see that you're going to have kappa 1 is going to be positive, and kappa 2 is going to stay null. So kappa 1 plus kappa 2 is going to change, even though you have applied completely, even though you have not really distorted the shape. You have just changed the way in which your sheet of paper is embedded in 3D space. So with this theorem, you understand that, okay, the mean curvature, it's really a 3D object. So it's not something that you can hope to generalize on graphs. On the other hand, the product between kappa 1 and kappa 2, this is intrinsic. This can be defined purely using geodesic distances on the graph. The way you can see that is that if you take your sheet of paper, kappa 1 equals 0, kappa 2 equals 0, so kappa 1 times kappa 2 equals 0, and if you fold your sheet of paper without tearing it, you see that at any given point, you're always going to have one curvature which is equal to 0. With a sheet of paper, if you do not do anything strange, you're never going to get kappa 1 and kappa 2 non-zero. Okay, so you see that in terms of intrinsic geometry, this is a quantity that is preserved. Okay, and so now the intuition that people have on this Gauss curvature or this Ricci curvature in high-dimensional spaces is that it is related to the way geodesic curves converge or diverge on the space. So let's take the example of the Euclidean plane. Here I have 2 points. I have my geodesic between the 2 points. So geodesic just means the shortest path, 2 points. And then I say, what if you have 2 points facing each other, and both points say, I'm going to turn by 90 degrees and I'm going to go straight. So point A turns to the right, goes straight, and point B turns to the left, goes straight. They walk at the same distance, and because we're on a flat Euclidean space, the distance between the 2 moving points stays identical. Okay? This is what characterizes null curvature. Basically, 2 parallel curves stay at the same distance of each other. Now imagine if you had done the same experiment, but on a sphere. Now you have this point, they look at each other. Point A says I turn right, point B says I turn left, they go straight. And what you can see is that the geodesics actually converge. They are going to meet here at the North Pole. So, this is a property that is only defined using geodesics, maybe angles too, but that characterizes positive curvature. And now, and it's also related to the fact that the volume of the ball, is not so large. Whereas what happens on my surface that has negative curvature, I do the same experiment. So A turns right, B turns left. You see that the geodesics diverge. And this is the main intuition about negatively curved spaces. Negatively curved spaces are spaces where geodesics diverge. So those are all pictures that are more than 100 years old. And mathematicians, like 40 years ago, tried to distill this intuition into a definition that could be extended to graphs. And so Mikhail Gromov, a very famous geometer, proposed one such definition. He said, what's interesting on hyperbolic graphs, on hyperbolic spaces like this one, like if you do the math, you can show that it is true, is that if I take a triangle, a geodesic triangle, A, B, C, and I look at the segment from A to C and from C to B. So I look at those 2 segments, AC, CB, and then I try to draw the segment from A to B. I can show that all along the path from A to B, I never step too far away from the 2 other sides of the triangle. Basically, if you define a delta neighborhood of the union of the 2 segments, delta neighborhood means just a point, the set of all points which are at distance less than delta to the segments, to the points of the segment AC and BC, then you can show that on a hyperbolic space like this one, geodesic triangles will always be thin in this sense. Obviously, it's something that is not true on a Euclidean space. You take a Euclidean space, a Euclidean triangle, you scale it, the distance, basically the point which is the middle point between A and B can be arbitrarily far away from the 2 other segments, because when you scale your triangles, your sides are not pushed towards each other. But on a hyperbolic space, this is what happens. And if you think about it, this is exactly the type of behavior that you find on a tree. Because on a tree, you only have, a tree is an acyclic graph. So on a tree, you only have one path to go from A to B, B to C, and A to C. So on a tree, actually, delta is equal to 0. The geodesic triangles on a tree are completely degenerate, in the sense that to go from A to B, you have to roll back from A to C, then find the junction, and then go from C to B. Okay, but this notion, Gromov hyperbolicity, the idea of extending this to non-zero values of delta, allows us to consider graphs that look like trees, but are not exactly trees. And the motivation for that was to study graphs that are associated to groups of matrices. So this is typically what we call a hyperbolic group. It's a group of 2 by 2 matrices with integer coefficients such that their determinant is equal to 1. Okay. So it's SL2 of Z. And if you display the Cayley graph of the group, okay, Cayley graph is like the graphical representation of a group, just like a square grid is a graphical representation of Z2. the group of integer pairs, you get this kind of graph, and you see that this graph, clearly you have cycles, like it's not exactly a tree, but you can also see that at a large scale, it behaves like a tree. Okay, and here delta seems to be equal to like 2 or 3. If you go from this point to this one and this one, like a geodesic triangle, you understand that this picture can be applied here. Okay, so this is the kind of idea that marinate in mathematical departments since the 1980s. But okay, this notion is very global. It's a property about large-scale triangles. And when we deal with real-life graphs, we don't expect such large-scale properties to hold. We expect that probably a graph is going to be the union of small subgraphs. So we are more interested in local notions of curvature. And so that's why people came up with suggestive analogous of curvatures for graphs, such as the Forman curvature. So the Forman curvature is defined for every edge of my graph here. So I have V1, V2. And the way I'm going to define the curvature is I'm going to take a constant 4 minus the number of edges that go to V1 minus the number of edges that go to V2 plus 3 times the number of triangles that have this edge as their base in the triangle. Okay, so just intuitively, what this formula tells you is that if there are loads of triangles, as in a sphere, you have loads of triangles, not that many edges, then you are more positively curved. But if you have lots of edges, like if this looks like a tree with lots of branching points and few cycles, then this is going to be essentially 0, but this is going to be highly negative. Okay, and so this formula, it's made so that on the plane it's equal to 0, and on a tree it's definitely negative, and on a spherical mesh it's definitely positive. So that's one possible definition, and currently people are defining like refinements of those heuristics that also give the correct values on different grids, like 3D grids, 4D grids, etc. Another alternative is to look at what we call the Olivier-Ricci curvature, which is defined using the theory of optimal transport. So here the idea is that it's also defined on edges on a graph. So you have your first vertex, second vertex, and you look at a small normal distribution centered around the first vertex and centered around the second vertex. So when I talk normal distribution, it just means a distribution which is centered around this node, centered around this node. And then I say, what happens if I transport this distribution to this one? Okay, so I'm not going to dive into details because I don't think that all of you follow the class on optimal transport, but the intuition. Let's say that here you had a normal distribution, and you are on the Euclidean plane. Then the optimal way of transporting this distribution to this one is just to translate it. And so you can show that every point essentially will travel the same distance as the two vertices. So this is a characterization of flat planes, where it's just the same idea as here. Like neighboring points tend to stay at the same distance as the base points. But now, if you were on a sphere, on a positively curved space, then you would have shortcuts. A bit like if you take the plane, you have shortcuts, and so on average, the transportation distance would be smaller, whereas on a hyperbolic space, like on a tree, imagine if this was the graph of the tree, points with neighboring points, if this point wanted to go there, it would first have to travel to the base point, then go there. And so the transportation distance on average would be higher. The transportation cost would be higher than just the travel distance between the two vertices. And so that's using this intuition and making some mathematical formula, we are able to generalize curvature to those metric spaces. So it's another way of trying to generalize curvature, at least to distinguish between flat, positively curved, and negatively curved spaces. So that's all well and good. But what I want you to take home from this lecture is that notions of dimension, positive, flat, and negative curvatures should be intuitive for you if you want to, if you want to understand current graph research, because this is the most basic way of describing the neighborhood of a point in a graph. And so maybe, I 3D printed some model where, this is what you should think about when you think of a flat space. Okay, so this is just a mesh where every vertex has 6 equilateral triangles as neighbors. And when you do that, you just end up with a piece of tissue. But now, positive curvature is what happens when you have fewer triangles. So you get these kind of things, and probably I should have made the calculation, but if you take this graph, this discrete graph, I would expect that this formula would be positive. Okay? And on the other hand, hyperbolic spaces are what happens when you have, like, instead of having 6 triangles per vertex, you have 7. And then you end up with this kind of salad. And that's why I say that trees are like salad, because trees are like hyperbolic spaces, and hyperbolic spaces look like salad. And maybe if you just look at this graph, you can play around it and then wash your hands. During the lab session, you see this object, you see that at every vertex position, you have 7 triangles, and you see that the natural way of embedding it in 3D space is to do something like that. You end up with a hyperboloid, with curvatures that are in 2 different directions. So Gauss curvature is a negative. Okay, so that's really, if you get that from today's lecture, that will already be great. Understand that continuous and discrete vocabularies are both useful to describe those metric spaces. Okay, and also, because I find that it's way too cool, I printed some of the some of those images. So that you see, it's real. Like, using just a polynomial of the curvatures, you are able to generate aluminum foam or blood vessels. So that's it for simple intuitions. And so now I would like us to look at global tools. Because here, we've described what happens if at every vertex I have positive curvature, then I get this. At every edge I have negative curvature, I get this. But now real life data sets are never that simple. And so it's very important when you get a graph or a high dimensional data set, it's very important to try to visualize it. And how can you do that? Well, the first idea would be to just use PCA, project it in dimension 2. But it doesn't really work, okay? Because if you do PCA on this, clearly you do not unwrap the intrinsic 2D manifold. And so that's why people, for a long time, have tried to design algorithms that take this kind of point cloud and recover you a nice 2D map. And the general idea behind them is that they will always try to first compute the graph of k-nearest neighbors, because the graph of k-nearest neighbors is the simplest way of describing local neighborhoods. They will compute the graph of k-nearest neighbors, then they will compute statistics on this graph of k-nearest neighbors, like how many neighbors do I have, how far away I am from them. So statistics on a high-dimensional KNN graph. And then they will try to optimize a 2D representation, a 2D point cloud, to make it such that the k-nearest neighbors graph of this 2D representation has the same statistical properties as a high-dimensional KNN graph. Okay. And so all the tools like ISOMAP, TISNI, UMAP, they are designed to create 2D point clouds whose k-nearest neighbors graph has the same statistical properties as your real KNN graph. Okay. And so I could show you the equations, etc., that are behind those models, but at the end of the day, all those models have theoretical background for why they chose this or this formula, but really the formula were chosen because they gave aesthetically pleasing results and that people were able to see structures and patterns in their data. So I don't think that you should understand those tools as through a theoretical lens, but more through a practical lens. And so that's why I would like now for you to just go on the UMAP website. So if you go on my webpage, if your internet connection works, you can go on my webpage, you can go in the webpage of the class, and you're going to find 3 links about UMAP tutorials. And maybe just read them, at your own pace and try to understand what is happening. Like, try to see the impact of the parameters, like essentially change the statistics that the algorithm tried to preserve, and hopefully it's going to help you to get a first-hand intuition on the model. Okay? And then at the start of next week, I'm going to show you how you can use it in practice. Like, how is it useful? But I'm not going to show you examples if you've never used it before. Okay, so if you have your laptop, it's perfect. Otherwise, we can go in the other room. Normally, Jupyter should work, so you should be able to use UMAP. And if UMAP is not installed, like if import UMAP doesn't work, you should write pip install UMAP -learn, pip install UMAP -learn, and in 5 seconds you should have UMAP animation.